Three types of heat transfer for 3C keeping warm. First one is conduction. Conduction will only happen in solids, and the way that the heat is transferred by conduction is when the particles vibrate when they're heated, and the vibrations in the particles of the solid will transfer that heat energy by hitting the particles next to them, and that energy will be transferred almost like a domino effect. So the vibrations will pass that energy through the solid and heat will be transferred from one place to another. Convection happens only in fluids, so it could be in liquids or gases. The most common example of where convection actually transfers heat energy is if you have a beaker of water or any fluid and you put the Bunsen burner underneath, then the particles that are closest to the flame or the heat source, they will be the ones that gain that heat energy straight away at the bottom. Then when the particles gain that heat energy, what they'll do is they'll spread out. So the energy will be increased with the particles, they'll gain more energy, so they'll move more, and if they spread out, they'll move away from one another and their density will go down. So if the density decreases in these particles here, they're less dense than the particles above. These particles will move to the top, or float essentially, and the ones above that are more dense because they have less heat energy will come down. Then they will take the place where the heat is, they'll gain the heat energy, and the same principle will happen. They'll become more energetic, their density will decrease because they'll spread out, and they will float, and then the process continues, and the particles will just keep cycling through this heat at the bottom until the whole substance has been heated, and this is what we call a convection current. So the convection current is this constant process of particles gaining energy, spreading out, becoming less dense, and then floating or moving to the top, and the more dense ones sinking down and taking their place, and then the cycle continues. Okay? Radiation. So radiation or heat transfer by radiation is transferred by EM waves. So the infrared part of this, the EM spectrum is the thermal energy that is transferred from one place to another, so heat energy, and it's transferred by the transverse waves and can be therefore transferred through a vacuum. So because EM waves can travel through space, they don't need a medium to travel from one place to another. It doesn't require any particles, unlike conduction and convection, to be able to transfer the heat from one place to another, so it can be transferred through anything, essentially. So solids, liquids, gases, and a vacuum as well. Radiation, we need to know basically that black, dull, or matte. So matte is like the texture of the material. It's not a smooth, shiny material. It's quite a rough, dull material. And black are good absorbers and emitters of heat. So for example, if the heat source was coming from outside and you wanted something specifically to take the energy from the outside, heat up and become warmer, for example, let's say you had a tank of water that you needed to heat in order to transfer that hot water for people's homes, then the best color that you could have if you were in a hot place would be a black container, because the black color would absorb the heat energy, it would absorb the infrared radiation, it would heat the water inside, and then you get hot water. But alternatively, black, dull, and matte colors are also very good emitters of heat. So if, for example, you have components in a computer or the engine parts in a car, you'll see 9 times out of 10 they'll be colored black. And the reason is because the heat that's coming from the inside needs to escape. You do not want the heat that's produced inside the electrical components or in the engine of a car. You don't want that to be trapped inside. The best way to get rid of the heat, to emit the heat from inside out, is to have the colors of all those components painted black. So black colors, very good absorbers, but also very good emitters, and it depends on which way the heat transfer is going. Alternatively, the white or shiny colors, so if you have reflective surfaces or you paint surfaces white, for example, in hot countries, you'll have the houses painted white on the outside. They're very good reflectors of heat radiation. So if you want to keep the heat out, then you'd paint the walls of a building white, for example, you'd have shiny surfaces, and the heat that's coming from the outside would not be able to get in because it would be reflected back out. Otherwise, if you want to keep the heat in, for example, the vacuum flask we're going to look at, if you have a hot substance inside, a hot liquid inside, and you want to keep that heat inside, then you put a silver surface on the inside, so the heat radiation would reflect back inside itself, and it would maintain that heat inside. So again, it completely depends. Is the heat coming from outside in, or is it going out from the inside out? Okay, and it depends on the colors. So black, good absorbers, emitters; white or shiny surfaces, very good reflectors of heat. Okay. Then, carrying on with conduction, there are three factors that affect the rate. So how fast can heat energy be transferred from one point to another through a material by conduction. The thickness of the material completely depends on how fast the energy will be transferred. So the thicker a material is, the slower the heat transfer is going to be, all right, because it will be harder for that energy to transfer across more material. The conductivity of the material itself, so the property of the material will have a specific conductivity, and the better the conductor, the faster the heat energy will be transferred. So the higher the conductivity of the material, the faster the heat energy will be transferred. And finally, the temperature difference from one side to another, or from inside out, or outside in. If the temperature difference, for example, on the inside of a room and outside is very large, let's say on the inside of the room it's 20 degrees Celsius, but on the outside it's 60 degrees Celsius, then you're going to have a heat transfer at a specific speed. But if you had 20 degrees inside the room and only 35 degrees outside, then actually the heat transfer wouldn't be as fast. So heat transfer from outside in, let's say, would be a lot slower than if the temperature difference between the two was much bigger. Okay, so the bigger the temperature difference between two places or two things, the heat will be transferred much faster. Okay, so they're the three factors that affect how fast is heat transferred by conduction. Insulating homes, so using all the ideas of conduction, convection, radiation, how can you build and design a building in order either to keep the heat in, for example in a cold country you don't want the heat to escape, so you insulate the home, or for example in a hot country you want to keep the heat out, so it depends on the conditions. You have double glazing windows, so you have literally two sections of glass in a window with a gap in between. Now, because conduction can only be transferred through a solid material, if you have two panes of glass with a gap between which is filled with only a little bit of air, there's no solid material between them, so therefore the heat cannot be transferred from one pane of glass to the other by conduction. So you're reducing the amount of heat transfer by conduction by using double glazed windows, which are just two panes of glass with a gap. Cavity walls, same principle. You build a house with two walls with a gap in between. And because you've removed the solid material in between the two walls of the house, heat will be transferred slower because of the fact there's no solid material, and also it's thicker. So you're doing two things to slow down the heat transfer using just a cavity wall, which is two walls with a gap. Problem is the gap between two walls in a building, it's so big that air can circulate between the gap, convection currents can occur, and heat can actually be transferred by convection instead. So you've got a cavity wall that prevents conduction, then you fill it with what's called cavity wall insulation, which is a yellow foamy material, which is a very, very good insulator, so has a very low conductivity. You fill the cavity wall with cavity wall insulation, that prevents that convection current from happening inside the walls, so you've just reduced conduction and convection. Something to add, this is also used in loft insulation, so you have lofts in the attic of a house. Again, there's a lot of empty space which is going to allow a lot of heat to transfer by convection. You're going to have a lot of circulating air transferring that heat energy, which is not what you want. Fill it with loft insulation. It's the yellow foamy material. The reason the yellow foam is such a good insulator is because it is technically a solid material made of about 90% air, a little bit like a sponge. It's a solid, but it's made mainly of air. And if the trapped air inside that material cannot move anywhere, one, mostly air, which means conduction won't happen. Two, the air is trapped, so it cannot circulate in those convection currents. And then you have carpet. Obviously, you put the carpet down on the floor. Again, you've got fibers in there that will trap the air. It will reduce conduction as well. It's a low thermal conductor, so it will reduce conduction through the floor and losing heat through the floor. And finally, you have a draft excluder, which essentially just put it at the bottom of the door. If you have a gap in the bottom of your door, then heat energy is going to transfer in from the outside, or you're going to lose it from the inside. If you block that gap, it's simply literally just a bit of cotton rolled up into like a cylindrical shape. Put it at the bottom of the door, and it will stop that convection from leaving through the door. The very last thing that you could be asked on this one is about the vacuum flask specifically. So it is literally a flask, a thermos flask. You either put a hot coffee inside it and keep it hot, or you put a cold drink inside it and keep it cold. A few features of it that actually make it a very good insulator of heat is the vacuum itself. Similarly to the double glazing, if there's no material between the two walls of the flask, then no heat can be transferred by conduction because there's no solid, it's a vacuum, it should be empty space. No heat can be transferred through by conduction. Put silver surfaces on the inside and the outside. Any heat from inside, if it's a hot drink, the radiation from that will bounce back off the silver surface, so it will be kept inside the flask, it will reflect, and anything from the outside trying to get in will also be reflected back out, so it will be kept out. You have a plastic stopper at the top. It's a good insulator, it's not a good conductor, and it prevents any convection currents that are created inside the flask itself. Let's say the flask is half full. There's going to be a convection current inside here. If there's no plastic stopper, it's going to leave, so you'll lose heat due to convection. It's also a bad conductor of heat, so it helps conduction as well. And then finally, there's a plastic spacer at the bottom. First and foremost, it's there for structure to keep the inside section of the flask fixed to the outside, and then it's plastic because it's a bad conductor of heat.